Welcome Mechanics of Materials students. In this lecture, I'm going to go over the basics of sort of a free-form beam design. So the things that we're going to consider for this beam are longitudinal stress due to a flexural type applied load. We're not going to include any kind of actual axial compressive or tensile loads. We're going to also include deflection. So we don't want the beam to basically the middle to sag too much or the ends to go up too much. And we're also going to consider shear, maximum shear. So we're going to look at longitudinal stress, deflection, and shear. And then we're going to compare those to the material properties and to the dimensions, length, height, and width that we could choose. And material properties are, we're going to look at our modulus, our maximum tensile stress, our maximum shear stress that we can support, what kind of safety factor we might want to use depending on the material and the nature of the application. Okay, the type of loading that we have in terms of just how our loads are applied, we've got a uniform distributed load from probably the weight of something that we're putting on top of this beam. This could be anything provided that its weight was being transferred with another stiff plate. So we could be looking at maybe something holding up a bridge, and then this distributed weight could be a bunch of cars, provided they were parked on a stiff deck. There's not a bunch of point loads from each car. We've got this uniform weight. And we want that to be adjustable. We want to see how much we can apply. So we want to develop some expressions where everything is adjustable, so we can match the load to the material and the dimensions of the beam. We're going to assume that the beam has some kind of weight. A lot of our strongest materials are regrettably, rather high density. So we're going to assume that our total distributed load is going to equal the sum of our applied load, what we are holding up with the beam, plus the weight of the beam, which I'm going to call a dead weight. Now, we can't go change it after the fact. So our applied load could be a dead load or a live load depending on whether or not it can be changed. But the weight of the beam itself is always a dead load, and that you can't change it on the fly. The beam is there. It is what it is. And these are both going to be non-variable along the length of the beam. We're going to assume that they're both the same. So we're assuming a uniform density, uniform material properties. The beam's going to have a cross-section height, and for those of you hopefully are familiar with our shear and longitudinal stress analysis, H is going to be that dimension in what we typically call the Y direction of the cross-section, and B, our width, is the dimension of the cross-section in the Z direction. And so we're going to assume X is our orthogonal direction that denotes the position along the length of the beam. So we have a beam that's H tall, B wide, it's L long. It is simply supported, so we have kind of a hinge support here and a roller support. This could be any kind of bearing. We don't have any loads applied in the X direction. Like I said, we're not applying any compressive or tensile loads, so the neutral axis is the centroid right here in the middle. And it's a rectangular cross section, so not very efficient from a density versus load bearing standpoint, but very simple to manufacture. So we're going to make a list now of the things that we would need to know for design. So we can start with number 1. And again, these are things that we'll of course want to compare to material properties. We're going to want to know specific weight. We'll start with our material properties, because we need that to calculate our dead load, which, depending on what applied load we have, could be a significant part of the overall uniform distributed load. In order to calculate deflection, we're going to need to know our tensile modulus In order to compare our longitudinal shear stresses, we're going to need our sigma yield. We're going to assume for now that we're going to be working with ductile materials, so we're going to be designing against yield, not UTS. So that's kind of what we've got on the materials side. So we can look at, for our longitudinal stress, longitudinal stress. So again, that's the stress sigma x that is due to flexure, that's due to the applied moment. So we use the flexure formula for that, of course, and we'll just sketch that down. So that'll be the moment wherever we are times the distance from wherever we are in the x direction to the neutral axis, which in our case is the centroid, divided by the moment of inertia about the z-axis. Okay, so from a design standpoint, we really don't care where it is just anywhere. We want to know where this is maximum. So we're going to compare that to max needed. So from our discussions of longitudinal stress in beams, we know that that will occur at y equals max distance in this case I'll just say neutral axis to tensile surface, which will be in this case the bottom of the beam because it's going to want to curve up, so our tensile side is the bottom. Our IZ will just follow the formula for a rectangle, and we'll want, we'll just sketch out what this is. In this case, we know that our neutral axis is going to go through the centroid, which is, from the standpoint of the y-axis, it's at h equals 2. So we can just start sketching this out. Y centroid. We're just going to fill in a few of these while we're at it. So we can say the maximum distance to the tensile axis, which is down here on the bottom of the beam here, is just going to be h over 2. And we can look up the formula for the moment of inertia about that z-axis for a rectangle is going to be 1/12 times b times h cubed. So we can use that here for IZ. And so of course we're going to want to know what the maximum moment is. We don't just want the longitudinal stress like as a continuous plot, although that would be nice to know. We want to know M max. We know from our statics that for a simply supported beam that's loaded uniformly, that's going to occur in the middle. So that's going to be at L over 2. And we can step through our statics and we can develop some expressions for shear and moment. In fact, we know that we're going to end up having, basically we'll call it W total. So that's our load per unit length times the entire load divided by 2 at each support. Beam length times total times, not plus. So if we go through our shear and bending expressions, our statics expressions, we can get an expression for shear at any x and for moment at any x. So our shear, and this is not our shear stress, but our shear force V at any x is going to be equal to negative W total times x plus that value at the support. I'm referring to my notes here as I write, because I've already worked this out. Our basic beam calculations. So we can say that this is going to be a maximum. We've got a line equation, so this would be 0, of course, in the middle. So our shear stress would go to 0 in the middle of the beam, and it is going to be maximum right beyond the supports at either end. So if we put in L, we have negative L plus L over 2 times the total distributed load, or if we put in 0, we just have L over 2. Same magnitude. We'll take a quick break here. Okay, resuming. So here is our shear. So we can just say we'll need to know max shear for our total shear expression. But for longitudinal stress, we need moment. So we can basically integrate this again between x and L, and we'll integrate the other side from the shear at 0 to the shear at any x, or from the moment at 0 to the moment at any x. Basically, we're going to integrate dv, dm, integrate dx, and we're going to end up with, not surprisingly, integral of a polynomial, W total times x squared. We're going to end up with a parabolic expression, concave down. No, constant of integration is 0 because neither support can give us any moment. So we know that our moment when x equals 0 has to be 0 because this pin support can't give us any moment. So this is our expression for moment. So that's going to be maximized basically where v is 0. V is our shear force is the first derivative, of course, of our moment. And so this is going to be max at L over 2. Okay, so we just insert L over 2 to get the maximum. I don't know if I have that in my notes here. If not, we'll just work that right on out. So we'll have total distributed load L squared over 4 divided by 2 total distributed load times L is L over 2 divided by 2. So we're going to have an L squared over 4 and an L squared over 8. So we end up with L squared over 8. Okay, so there's our M max. So basically we know that we can already predict we're going to have a squared relationship between beam length and max moment. Moment is linearly related to longitudinal stress, so we already know we're going to have a squared relationship with beam length. So if we end up having a set applied load, we pick a material, we pick a cross section, then basically our longitudinal stress is going to be a function of how long the beam is. So we'll be limited on how long we can allow that span to be and still remain within our allowable tensile yield. Okay, so that's That's our checklist for longitudinal stress. So the next thing we'll be wanting to consider is deflection. So we know that the deflection angle, literally the shape the beam makes as a function of its position. So basically we'll just draw a little picture of this just to refresh ourselves. So we're pretending that the end of the beam is kind of sticking up because it's deflected, and here's our original horizontal axis. So the beam's deflected because we stepped on it with a big load. So this angle. So the change of that deflection angle with respect to x is equal to the moment at whatever x we're at. So this isn't a max moment unless we're at a max rate of change of deflection, divided by the modulus divided by, this will be Iz. So here's another case where a bigger moment of inertia is our friend. It's our friend against longitudinal stress, and it's our friend against deflection. So if we want to get actual deflection anywhere along the beam, and this is little v, so this isn't internal shear force, this is deflection in length units, we're going to end up integrating. So our deflection at any point is going to be our deflection at 0. So that will be double integral. We're going to integrate once to get our angle theta, integrate again to get our deflection. So we'll need our x-dependent moment expression, so we'll need this over EI. A lot of times you'll see this written just EI. Plus, and of course when we integrated once to get theta, our angle theta, we ended up kicking out a lower limit of integration, our theta at 0. So we'll integrate that again. And this is just a review. For this, I'm assuming that you've already gone over this material, and so we're just kind of putting it to use. So in order to evaluate this, we already have an expression here, and we know what our modulus is, presumably, when we pick our material. Our moment of inertia about the z-axis, of course, is dependent on b and h. And we don't know what our deflection angle is at 0, because we don't know what kind of wild shape this is going to take. You know, that's going to depend on our loading and everything else. But we do know that it's pinned down. It can't actually stick up that way. It's pinned down at the ends. So we may not know what theta is doing at those endpoints, but we do know that our little v at 0 and at L equals 0. So we can use those two boundary conditions, those are called boundary conditions, to evaluate theta at 0 and to evaluate any constants of integration that come out of whatever we integrate. So we can start with this is 0 and then use our use v at L to basically backtrack and get theta at 0. So we can crank through a whole lot of math, maybe not a whole lot. We can crank through a few integration expressions. I'm not going to necessarily walk through all of them, but what we're going to do in our case is we're going to integrate this twice, and then we're going to do some algebraic solutions with our boundary conditions, and we're going to come up with a total final expression for our maximum, our V max, which will not surprisingly occur for this type of loading and support, will occur right in the middle. The beam will basically end up kind of sagging between the 2 points of support. So if we are designing around a maximum deflection, we're going to find it in the middle. So from the standpoint of a corner of the box design, we really only need to know what the deflection is at the position, the x position of maximum deflection. So that turns out to be, if you go through the double integrals and you include all of the constants, -5 over 384 times our total distributed load, is L to the 4th, over our modulus times our moment of inertia. So basically, to get this, I only needed my expression for moment as a function of position along the beam, my modulus and my elastic modulus, tensile modulus, and moment of inertia for the cross section don't change with position. It's a uniform beam. If they did, they would just end up in the integral, but they're not, so these can actually come out. And so I'm just integrating this expression twice and then using these boundary conditions. So basically, I now have what I need to calculate longitudinal stress and deflection. I'll erase my little picture of my deflected beam since I know where it's going to deflect. So the only thing that I need to do now is work out an expression for maximum shear. And in your sections on shear stress, you probably learned that in a lot of cases your maximum shear, kind of unlike longitudinal stress, is going to be found near the centroid or near the neutral axis that something is deflecting around. I'm just going to review this. This is average shear stress at the cross-section plane area that we're considering. So this isn't a point, this is average over the area we're considering. It's going to be our shear force, which is why it's really important to know where this was a maximum. And again, this is now I'm going to write this out from the basic equation. I'm going to take a step back. So shear stress, average shear stress times the width of the plane that we're considering, which in our case is B. So the average shear stress across this face times the width of the face B is equal to, referring to my notes, shear force at whatever given x position we're looking at, divided by, again, our moment of inertia. Notice this comes up in every limiting expression. Now we know why things are designed for big moments of inertia. Times Q, which is a function of the area of that, so that total cross-section area, and the distance of the y position we're considering when we're calculating our shear from, so its centroid relative to the centroid that we're concerned with. So in the case of our beam, our Q ends up being, I'm just going to write out my expression for Q in our case, h over 2 minus y times h over 4 plus y over 2. And I got that by remembering that I can calculate So I'm looking at the cross section of this beam, and remembering shear is a little bit weird, because what I actually do is when you derive the expression for that tau average, that average shear stress, you actually kind of use longitudinal force to put this little slice up here in static equilibrium with the rest of the beam, and you figure out, remembering that shear has to zero at the corners. So I'm looking at this little slice, and so look at the bottom. So my y in this case is this dimension. This is h over 2. Of course, this is b. And so what I've done is I've looked at the area of this little cross section and its centroid position, which is going to be h over 2 minus y, half of that, plus y. So that all equals h over 4 plus y over 2. So this is all calculating this Q factor that we need to calculate shear. Basically showing you where that's coming from. So if you multiply all of that out, you get b times h squared over 8 minus y squared over 2 so tau average shear times the width of the surface over which it's applied. Signs are less important from a design standpoint. We're going to be going for what is the maximum magnitude. We're less concerned with what direction it's going in, so this negative is less important from our standpoint. So we're going to end up with our b times h squared over 8 minus y squared over 2. And we're going to write out the expression for our moment of inertia, our 1/12 b h to the third, because unlike some cross-sectional cases, these two b's cancel, but we've still got a b in the denominator. So in this case, unlike where we had over here, we still had some dependence for our longitudinal stress on b. Then it was rolled into our moment of inertia. Some cases of shear, we do or don't have it, depending on the shape. We do or don't have a dependence on b. We definitely retain it. So it's less consequential than height, but definitely widening the beam is going to give us a little bit of advantage in reducing the shear. So y is basically, again, kind of the same as in longitudinal. It's our distance from the entire cross-sectional surface centroid, where the neutral axis is going, even though neutral axis is not as important for shear. It isn't really consequential. So we're going to get a tau max at y equals 0. So basically this term here is going to be a maximum when y goes to 0. So that y max, or excuse me, that tau max, just keep giving ourselves a little more room. So our tau max is going to be V max, which we'll see right adjacent to the supports, times h squared over 8 divided by 1/12 bh cubed. So this will probably get retained in our moment of inertia expression, but you can see that we're going to end up knocking off one of these. So our shear will be linearly related to the beam height, the actual height, top of the beam to bottom. We didn't have that as much up here. We had basically in our longitudinal expression, if you look at our y halfway from the neutral axis to the top or bottom surface, you're going to have basically 1h. It'll cancel with one of the cubed h's. So you've got a squared relationship of beam height in longitudinal stress effectively, but only linear with shear. So making that beam tall, bottom surface to top surface, is going to be more consequential for our longitudinal stress. But we can get as much bang for our buck widening the beam as making it tall if shear becomes limiting. So I've kind of increased my writing size as I've gone along. So I think that is all I am going to need. I'm going to just do a quick red circles here. So basically, in terms of the things I need, I've got this with these two defined. I've defined my max moment. I've got an expression for my total distributed load. I've got max shear. I could write an equation for max shear. It will be at the ends. So total distributed load times L over 2 B max. These are all expressions that I'm going to need. My total deflection, which is the first place that I pick up something from Hooke's law for our material. And here's my max shear. So basically everything that's circled I would need to put into a spreadsheet or some kind of calculator that would automatically calculate based on something that I populated with these values. Actually, it could calculate that value, but I would apply these values: H, B, applied load. I would look up my modulus for my material. I would decide how long I want to make the beam. I think pretty much everything else will flow from that. Then every other characteristic of my material basically tells me, have I exceeded it or have I not exceeded it? So I'm going to pause really quick and I'm going to switch views, and I'm going to show you how I just took these expressions that I hand calculated, that I used all of the information in my mechanics of materials studies for beams, and I solved them for the specific case: simply supported, uniform distributed load, rectangular cross section, uniform modulus, uniform density, and put them into a format where I can adjust anything and threw in a few values for a hypothetical material. Okay, at this point, hopefully you are seeing a reasonable view of an SMath MathCAD spreadsheet, and this is where I took pretty much all of the equations for beam dimensions, supports, loading, material properties, and then our calculated expressions for moment of inertia, for longitudinal stress, max shear force, max moment, internal moment and shear, and then max shear stress and max deflection from the start that I showed you on the tablet, and put expressions in which could be varied at will. So the goal here is to determine what parameters fall within an allowable range. and give ourselves the ability. This is basically a design guide. So I've started with material properties and applied loads. So each one of these is a variable input. So specific weight, this is, I think I picked this for brass. And here's the modulus in gigapascals, 100 gigapascals. It has a 420 megapascal yield. So if I'm going to look at my beam design, I'm going to be looking for my sigma XX flexure, and I'm going to be wanting to keep this below a certain fraction of this. So if I'm looking at this right now, it's pretty good. I have 8 times 10 to the 7 versus 1 to something times 10 to the 8. So I've got a safety factor of something like 10. Here's my applied load. I call this W sub 0. So this is uniform load per unit area, weight per unit area, or excuse me, per unit length. Now I've got my beam dimensions. Here's my width, which right now I have set it at 2 centimeters. Height is 12 centimeters, and then I'm looking at a 10-meter span, length span. Here's my moment of inertia, 1/12 base times height, and specific weight of the beam is going to be a function of and this is specific weight per unit length. So I'm going to calculate to get the total weight of the beam. I would multiply by the length, but because I'm expressing this as a uniform dead load, I don't want to multiply by the length of the beam. I just want to have basically a weight in newtons per unit length. So I just multiply the area, which is base times height, times that specific weight in newtons per cubic meter. And I notice that my dead load from just this material weight, so this is a fairly dense material. I've got some 2 centimeters by 12. It's got a much higher weight per unit length than I'm trying to hold up. So this is a very inefficient design. Here's where having an I-beam or maybe using a material with a lower specific weight, a lower density might be helpful. But this is an example of why, depending on what your scenario is, it's very important to consider material weight. Metals, concrete, things like that will tend to have dead loads due to the material weight itself that could be significant compared to what you're trying to hold up. Things like composites, fiber reinforced materials, even wood might be less significant. But it's always good to check, especially if you're pushing a safety factor, which you should never do. Max internal shear force and moments. So these are copied straight over from our earlier calcs. So shear max and max moment. This should have had a 2 divider in here, depending on how I define these. So these again are copied straight over from my tablet. And here's our flexure formula. Here's our Y, max moment and moment of inertia. Shear, we've got our max shear, and then the simplified expression that rolled out of our derived expression for Q, and then here's our 1/12 BH to the third. And again, max deflection, the result of that double integral and insertion of our no displacement at the two ends boundary condition. And so this will automatically calculate. So the trick here would be to basically understand what the objective of the design is. Do we want to do we have a set cross section that's available to us? If this is a mill product, we may only have a few defined cross sections available. Do we want to change the material? If so, we're going to change specific weight, modulus, yield strength. Do we care about how much we can hold up? presumably we are putting this beam into place to hold something up. So this one value here represents the entire purpose of the design, if you want to think about it. And you would presumably want as much of this as possible for as little material total, and also as little material weight as you can get, because that material weight, of course, adds to the carbon footprint of manufacturing, bringing to site, and possibly even end of life disposition. Our safety of use, our safety factors will come into play when we compare our material yield strength. We're not designing for fractures, so we're not looking at ultimate tensile. We're just looking at yield. We would basically knock this down by an appropriate safety factor. So we'd knock it down from 420 to say 210 megapascals if we wanted a safety factor of 2. And then we would compare that to our longitudinal stress. For shear, of course, we would compare the equivalent shear stress for this tensile stress, so we'd have to knock that down by a factor of 2 to get the equivalent shear. We'd have to basically do our uniaxial Mohr circle and then knock it down again for our safety factor and then compare that to shear max. So this is a bit of a rosier face than we'd want to see. We need to we have to apply, this is sigma tensile yield, we'd need shear yield. And then deflection would be an absolute value specified by the design. You know, how much do we want those beam ends to come, or to beam middle, the beam middle to sag. If it was a bridge deck, that would be a place water could accumulate, not good for traffic or for pedestrian safety, and not good for corrosion if we want to keep things dry most of the time. Not underwater. If it sagged a lot, we could start accumulating a snow load, which would mean that this might be higher than it was intended to be. Roofs can fail because of that. So deflection is very consequential depending on the nature of the design. So depending on what the end use was, we would be given a number and told to stay within it or less. So this would be a maximum number. So giving an idea, this what's fun with a design aid is we can basically play one factor off against another. So things that we could change, for instance, and I will just change things on the fly. If we wanted to go to, say, a material that is a lower density, like I said, I think I pulled this out of my materials handbook. This is brass. Not something you would necessarily make a beam out of. Some copper beryllium alloys, maybe, but you would only tend to use copper-based alloys if you were in a marine corrosion limited scenario, in which case they actually might work great. But generally we'd want something that's a little lighter, so maybe we'd choose a ferrous alloy or maybe a titanium alloy. That might be significantly less. So let's go ahead and change this. Oops, much easier to change. We've plugged our keyboard in. Let's take a pause. Okay, so we've changed the specific weight. We've gone to what is presumably a much lower density material. We've gone down from 83 to 40. So now we're looking at the specific beam weight is now on comparable to the applied load rather than being double. So we can work that through. That we would expect that to have more or less a linear effect on everything else. So we can see we went from something around 7 to around 5 times 10 to the 7th pascals for our longitudinal stress. Shear stress dropped a bit too. We saw a big change in our deflection as well. That was about a 50% drop. Unfortunately, typically when we go to a lower density material, especially aluminum or titanium versus a ferrous material, we will generally also get a drop in modulus, at least 25%. So let's be conservative and say that we're going to go down from 100 to 70. So we now kind of lost a lot of the advantage that we had otherwise gained in flexion. And nice thing, if we go to a heat-treated aluminum or certainly to titanium, we might get a much higher yield stress. So if we're looking at comparing our sigma to that, we're going to have a big benefit. We're going to leave our applied load where it is. Let's take a look at the effect of changing beam height. So that's going to be our bigger knob when it comes to our longitudinal stress. If we went to something that is closer to like a box beam, so like a square bar, let's go to a 2x2. We can see we've got a couple of things changing. The first thing that happened is our total load is much smaller now. Our dead weight is now only 10% of our applied load. But we would have thought that would have benefited us, and unfortunately we can see we went from having something like 1/10 of a meter deflection to having 16 meters of deflection. So it's actually almost bent double. That is, we would have yielded at this point. This is an unreasonable number. This is way past yield and probably into failure. And the reason for that is our height is a cube term in our moment of inertia, and that's down in the denominator of both of those expressions. So basically a box beam cross section or a square cross section just isn't going to work for this, not for these loads. Might be tough just to hold the beam up under its own weight. So we're definitely going to have to go to a rectangular cross section. Put that properly. So let's see if these numbers are more reasonable. This is still pretty high. This much deflection could be beyond the elastic range. Remember, our expressions for deflection were derived for small deflections, small angles. So this might have yielded, and it could be well beyond what would be allowable anyway. That's 3/4 of a meter. I don't think that we would want that much deflection. And we are also getting much closer to our yield strength. We're now within 2 orders of magnitude and not as bad on shear. So we definitely can do ourselves more good with that beam height term pretty much than anything else. And in fact, if we go up to something like 15, we can make our deflection almost inconsequential and possibly even sacrifice a little bit on width. Now there are lower limits on width to height, and that is related to buckling. So eventually if you get something that's a skinny ribbon, it will be impossible not to have twisting loads, which we haven't considered. There always would be. So I think a 1 to 15 is probably not reasonable. And this is where your structural steel shape guides are usually great places to start on. What base to height is even going to act like a beam with this loading? So chances are that would not be reasonable, and in fact we might be constrained to something more like 4 to 15 would be a little better. And what we're seeing as we change these two, the more we change the base and the height, the bigger we make them, the bigger our dead load becomes in this case, even with a lighter material. So that's an example of why an interactive design guide is important, but also just a general knowledge of what things are linear, what things are squared, what things are cubed. So when we want to change or evaluate the impact of any one variable change, a dimension, a material property, we know what magnitude of impact it's likely to have and whether it's going to be causing which things to go up or down. In a lot of cases, we have things that unfortunately become limiting. Eventually, we're simply not going to be able to make that beam cross-section bigger and bigger and bigger for a given beam material density, because eventually the dead load will make the applied load insignificant. So And that's where we may have to step away in that case from a rectangular cross-section entirely and go to something that's more efficient if we were constrained, especially to something with a high specific weight. So that's a lot of talking through and some steps through a way that you can put your flexure formula, your expression, derived expression for average shear stress in the maximum shear location in the beam, and max deflection to use in their corner of the box maximum positions along the beam, and in the case of shear and flexion, and longitudinal stress at their maximum positions on the cross section, which are not the same for either one, and do a corner of the box design. And there's a lot of things you can change with that. Now remember, if you change your cross-section shape, you have to go back and rederive. You'll still have the same maximum shear force, internal shear force, and internal moment, but everything that depended on that beam shape, so your Q factor in your shear expression, and of course your IZZ and your Y in your flexure formula, will change as well. So you have to go back and basically rederive those and put them in your spreadsheet. Some calculators, of course, you can, if you're doing this as a program, you could have those as subroutines. So you could call in a shape and name them different things and then call them into your general design guide. So there's all kinds of ways that you could make something a little bit more elaborate that gave you some more flexibility with your design. But it all starts with identifying what you need. You start with your beam length, its cross-sectional shape, understand the material properties that will be important, understand that you have, in the case of a beam with simple loading, we're not twisting the beam, we're not giving it any side loads. You have three types of stresses you'll worry about, and basically strains, deflection. So you'll have longitudinal deflection, you'll have shear stress, longitudinal stress. You're designing against yield or maximum displacement for those. So that is the end of my hour-long just walkthrough of a simple beam design guide, and how I took a look at different ways to evaluate consequences of shape change and material change for a simple rectangular beam, and kind of reinforced live why lightweighting is important for materials, and better idea of why all of those beam cross sections were taller than they were wide. So hopefully this helps you out and gives you an idea of how to use some of the great software to take all of the ideas that you have learned, hopefully about beams and torsional shafts in your mechanics of materials class, and put them in a format that you can really put them to use for design and analysis.